Okay. I'm going to let Athol do the introduction to Michael Strauss, but I just wanted to say a couple words, just as NCSA director, how pleased I am that we're continuing this colloquium series. And this particular project, that's shown here, the LSST project, which we'll hear much more about, and survey astronomy and how it's going to revolutionize not just astronomy, but I think it's a new way of doing science. And NCSA is very much at the forefront of this with the data services pipeline for both the Dark Energy Survey and the LSST project. It's something that I'm just personally very, very excited about. You've heard me talk about this a lot. I was at the NSF, and I was very privileged to help bring this project, after many decades actually of thinking through what this project could be, to help bring this to fruition for the FY14 budget start. And I'm going to just sit back and listen to the talk, but I'm going to let Athol do the introduction from Michael.
So thanks, Ed. It's a singular pleasure to invite, to introduce Professor Michael Strauss, Professor of Astrophysical Sciences at Princeton and the Associate Chair of the department there. Michael is an extremely important person in the LSST project as the Chair of the Science Advisory Committee. He has an impeccable and astonishing record of research in survey astronomy and other areas, and we very much look forward to your talk today. Thank you, Michael.
So thank you very much. Can people hear me? It's okay. Okay. So thank you very much for this invitation. Very happy to be here. NCSA, as you all know, is playing a very key role in LSST, and so I feel a little bit like I'm carrying coals to Newcastle by giving you this talk. But hopefully there'll be some insights they'll be able to give. And what I want to do is put the LSST in a slightly larger context. That is, understand where it came from astronomically, what's motivated, what its predecessors were, and what's happening between now and the time of LSST. So we're going to step back a little bit and go back to the early 1990s, when people started asking the question, what's the right way to map the sky as we carry out surveys? The Sloan Digital Sky Survey, which has been much of my life for essentially the last 20 years, was the first really modern CCD-based wide-field optical sky survey. And I wrote that sentence being very impressed, but then when you put so many adjectives in front of something, you sound like you're sort of narrowing things down. But in fact, as I'll try to emphasize, all those adjectives are really important. What SDSS did was cover about 14,000 square degrees, which is about a third of the full celestial sphere, in 5 photometric bands, and using CCDs, modern digital detectors. And so let's just remind ourselves where we were before that time. The state of the art before that time was for wide field imaging, if one really wants to make maps of the sky, was photographic plates. And electronic detectors allow us to just go to a just make it an important step forward. Electronic detectors are much more sensitive, and we'll talk about just how deep things go. But a number that we'll come back to is that the magnitude limit of the SDSS was roughly 22.5 in the R band, around 6,000 angstroms. Very linear response, allowing one to do very accurate calibration, very large dynamic range. Photographic plates are notoriously difficult to do calibration. Sensitivity over a very large range of wavelengths, allowing one to measure light in a variety of different filters. And data in a digital form that allows you to do sophisticated image processing, and which is, when you have a photographic plate, actually manipulating that information is much more of a challenge. So SDSS itself was made possible by 3 technological revolutions. The first is indeed the wide format CCDs. Indeed, before the SDSS was getting started in the 1980s, the thought of doing a wide field survey with CCDs was really was beyond what people could imagine, simply because the CCDs were too small. You get a tiny field of view at any given time. But with wide format CCDs, you can put 10 to the 9th pixels onto the focal plane. And we'll see just how far we're going to get as we go into LSST. You need a telescope design that also gives you that wide field of view. It's not just enough to gather the photons in the focal plane, but they have to be in focus all the way across. And that was a true challenge. And then you get terabytes, and as we'll see for LSST, petabytes of data. You've actually got to process that. And it was not until the 1990s that we had either the computational power nor the algorithms to actually produce the astonishing quantities of data that we're talking about. So the SDSS, to summarize 15 years of scientific work, it's been in operation for 15 years. It's still going. And it hasn't had an enormous scientific impact. So just statistics, to throw out 6,600 refereed papers to date, 300,000 citations, which really is quite remarkable. We're giving the Hubble Space Telescope a run for its money on these. They're still a little bit above this. We may still catch up. Hundreds of PhD theses, including a few people in this room. And it's made major discoveries in many, many different areas of observational astronomy. And a theme that I'll be coming back to is that when one does really big surveys using new capabilities and does it well, one does it really calibrates the data well and really understands what one has, that you end up allowing yourself to make discoveries in fields that you didn't even anticipate when you got started. And that is something that has happened time and again in the history of astronomy, that you build a new facility to do some kind of specific project, but by opening up data in ways that you haven't had before, you get discoveries that were simply unanticipated. And that's the wonderful, I like to tell prospective students who are thinking about majoring in astronomy, I said that one of the great things about astronomy is that we're so incredibly ignorant about the universe, and makes it, in some sense, very straightforward to make amazing discoveries, because you go take a look and there's always new things to discover. So that in a few slides summarizes the last 15 or 20 years of my life, and indeed the Sloan Digital Sky Survey. And what we want to do now is sort of ask the question, what's next? What are the new frontiers? So one of the things that the astronomical community does every 10 years or so is carry out what they call a decadal survey, where they ask themselves, what are the most important scientific questions that we want to try to address over the next 10 years, A, and B, what are the facilities that we need to build to make that happen? And so the last round of this decadal survey process found itself asking these kind of questions quite a lot, and we'll go through the details of this in just a bit. As you all know, one of the great discoveries over the last several decades has been that the majority of matter, mass energy density in the universe is in forms that are invisible to us. We call them dark matter and dark energy, and there's also dark baryons. And understanding what that all means, and using astronomical probes to quantify in detail what the physical nature of the various dark components of the universe require studying supernovae, the large-scale distribution of galaxies, gravitational weak lensing. We'll come back to all these things briefly as we go on. So that's one family of questions. We're realizing that the Milky Way galaxy is much more structured than we had realized before, and it's giving us crucial clues about how the Milky Way itself formed. And one learns more about that by mapping the distribution of stars, especially the fainter stars in the outer parts of the Milky Way. The variable and transient universe is much more interesting and complicated than we once thought, and surveys that are ongoing now are revealing all kinds of new types of explosions in the universe that we hadn't quite understood before, and the discovery space is just starting to open up. Mapping the evolution of galaxies and quasars with cosmic time, which is where a lot of my work is, and understanding the structure of our own solar system, asteroids, including those that might hit us on the head. So we're going from the scales of the solar system to the universe overall. But if you ask yourself the question, what are the data that you need to address all these questions, you come to the same conclusion. You need wide field imaging on a really large telescope. Wide field because we want to cover a lot of the sky, and we'll explain in a moment why a lot of the sky at once is a good thing. A large telescope because we want to look at the faintest objects. And we want this system to be very powerful so that we can observe over and over again. And so we not only do we want a large telescope, but we were going to be very greedy, and we want that telescope all to ourselves in order to carry out we're not going to do this in a half-hearted way. So that leads us to the Large Synoptic Survey Telescope, and this is a few slides of the history. So again, this project was born from the realization that all these science themes, which are some of the key questions covering a huge range of different areas in astrophysics, all require a data set that a single telescope can do. And indeed, it's the same data set. You can use the same data to address all of that. When you take an astronomical image, and we'll see some a little later in this talk, when I always like to tell my students, it looks as if the galaxies and the stars and the asteroids are just painted on a two-dimensional screen. And so you get the asteroids and the distant quasars all in the same picture. And then, of course, the great fun is sorting them out and getting all that wonderful science from those images. The project, which is now called LSST, was first envisioned in the late 1990s by Tony Tyson and his collaborators as what he called at the time a dark matter telescope, and focusing on the weak lensing, about which we'll have more to say. But again, the data that you gather become much more powerful than merely solving the question of what the distribution of dark matter is, and we'll see about that. And in 2000, the Decadal Survey, this process of setting priorities, advocated for this general idea. They called it the Large Survey Telescope. And in 2010, this specific implementation, the LSST, was ranked as the top large ground-based facility. And the many steps had to happen in between, but this was formally approved for construction by the NSF and the Department of Energy over the last year. NSF in 2014, Department of Energy just weeks ago, I think. And the total cost, when we can talk more about this, for construction operations is close to $1 billion. This is big science indeed. So what I want to do now is just talk a little bit about those various science themes that I outlined very quickly. Just give you a flavor of some of the issues and opportunities there, and then we're going to go into the specifics of the LSST. So it says weak lensing. What's actually shown here, it's a picture here from the Hubble Space Telescope of a cluster of galaxy in which background galaxies have been distorted in strong lensing. That's how you can see it visually, into these arcs that you see just everywhere in this image. So what's happening is that the gravitational field of all these galaxies and their associated dark matter are systematically distorting the images of these background objects. And this is an effect that is predicted from Einstein's theory of general relativity. We're directly seeing general relativity in action here. And in fact, with a little bit more imagination, the fact that these arcs here appear far away from where the densest part of the galaxies are is also showing us directly that there's a lot of dark matter in this. So with this single image, we're seeing both dark matter and general relativity demonstrated to us, and it's really quite dramatic. In clusters of galaxies, the effects are strong enough so that galaxies get enormously distorted into these arcs. A little further away, the effect is much more subtle, and that's indeed what we call weak lensing. And so clusters of galaxies, fascinating though they are, represented a small fraction of all the mass in the universe. If you really want to go measure where all the dark matter is, you have to go beyond the clusters and get out to the weak lensing regime. Weak lensing is tricky and this is a demonstration of why it's a technically challenging thing. Unlike the picture that we just saw, where galaxies are spread into arcs, a galaxy will be somewhat distorted, weakly distorted, and even here it's greatly exaggerated. It's typically about a 1% effect in the ellipticity is sort of a typical number. It's worse than that because, of course, you don't know what the original galaxy looked like. You only observe this. And so you don't know what the transformation is. So we're going to end up having to do this statistically. But it's worse than that because we don't observe this. We observe a galaxy having been seen through the distorting effects of the Earth's atmosphere, which smears things out. But it's worse than that because, in fact, the image is pixelated. We get individual pixels. But it's worse than that because there's shot noise in your image as well. And so you don't even have that, but you don't have the distorted image. You have a highly pixelated, noisy, blurred version of this. And you're trying to measure a 1% effect in the shape of this guy. And of course, there's no way to do that galaxy by galaxy, but if you can do this statistically over thousands and indeed millions of galaxies, hundreds of millions of galaxies, there's all kinds of wonderful signals to measure. I will leave off the bottom, which is how you start to get a handle, at least on the atmospheric piece of this. So one of the games that one plays is measure a correlation function. You ask the question, how is the distortion of the average of these galaxies over here related to the distortion of the average of these galaxies over here? And you do that as a function of the scale at which you're looking. And what explaining this in detail will take a little bit of time, but this represents the angular scale in the multiples. So we're going to smaller scales as we go to the right. And this is a measure of the strength of those correlations as predicted for three different sets of galaxies. That's what's shown here in the different colors, and two different cosmological models that differ in the properties of dark energy. And for the aficionados, the solid line is for W equals -1, the so-called cosmological constant case for dark energy, and the thinner line is for W equals -0.9. And so, again, for those people who work in the field, what you're supposed to see is that given the error bars that LSST will be able to measure these kinds of effects, distinguishing between these models will be duck soup. It'll be very straightforward, easy to do, and we'll be able to do much more refined versions of these calculations. Another theme that we talked about is the structure of our own Milky Way. Donna Cox just showed me wonderful movies in the visualization lab of the growth of galaxies, showing that galaxies and the Milky Way is presumably an example of this, have grown by the accretion of companions. And so one expects that the outer parts of the Milky Way still show the remnants of those processes and a great deal of structure in the distribution of stars. And that has been borne out by studies, in this case, an image from the Sloan Digital Sky Survey. This image is called the field of streams because, and it looks better on my laptop, one sees streams of stars, a variety of streams of stars that are understood to be the tidal remnants of galaxies that our own Milky Way has ingested. And one also finds these compact groups of stars which are dwarf galaxies in and of themselves. The SDSS is able to only go out to a few 10 or 20 kiloparsecs in these kind of studies. So getting to the nearer part of the outer part of the Milky Way, as it were. All the fun really should start as you get further out. As we'll see, LSST will go something like 5 magnitudes fainter, which gets you another factor of 10 in depth, or another factor of 1,000 in volume that LSST will be able to explore. And so there's any number of interesting questions to study there. I will not talk. This is a very complex plot that quantifies the statement of just how deep things go, but I think I said it all in words, so I think I'll skip that. The variable universe we've talked about. Again, this is a field that is exploding, pun intended. On one axis, I show here the time scale of any specific kind of variable event, or in this case, decay time for some sort of transient explosion and how long it takes to decay away. The y-axis is absolute magnitude or luminosity. And this is a snapshot now somewhat 5 years old and somewhat outdated, what is currently understood to be all the different flavors of objects that are known to explode in the universe. There's a third axis that of course, is hard to show on a two-dimensional plot, which is the rarity of any given type of object. You'd like to know, if you want to find rare objects of various sorts, you need to explore, you need to survey large chunks of the universe and do so very often to be lucky enough to find those rare events. So again, the qualitative point that one wants to draw here is that each of these boxes, many of these boxes are new discoveries in the last 10 years or so. And given the rate of discoveries, we know there's a lot more to be done. And LSST, as we'll see, will give us the ability to go explore this parameter space, and in particular explore that third dimension that's not shown here, the dimension of rarity, which sometimes those rare objects may indeed really hold crucial clues about the physics of exploding stars or various other things. We don't know. This is probably the area where if we were to ask about the known unknowns, this is the this is the case. This is the area where we know we will make discoveries. We just simply don't know what they will be yet. On dark energy, we think we're just going to measure that quantity W to a few more significant figures. Maybe that's all that will happen. And here we sort of know that we're going to discover things we don't know what they are yet. The known unknowns, indeed. Okay, and just one more of these, going through the scientific themes that we were talking about before. This is again a plot from the SDSS. Theme again being that LSST sort of picks up where the SDSS left off. So what's plotted here? We're looking at asteroids in our own solar system. Each dot represents a single asteroid. Asteroids are characterized by their orbits, and so two key quantities are the semi-major axis, how far they are from the sun on the x-axis, and the y-axis, the sign of the inclination relative to the orbit of the Earth, where most of the planets lie. And the first thing that you see is that asteroids seem to find themselves in various clumps of common orbit, sometimes called families. One of the things that the SDSS was able to do is, in addition to mapping up and understanding something about the orbits, it was able to measure the colors of these asteroids by measuring in multiple bands. And the color is telling you something about the surface composition of these asteroids, what these things are made of. And the colors are represented in garish pastel colors here on the image. So all the things that look lilac here or purple are all indeed of the same astronomical color. And what this image shows us, for the first time indeed, is that objects in a given dynamical family, that is, with given common orbits, tend to have similar colors, similar chemical composition, which suggests that these families some of these families, many of these families, probably came from a single parent body which was chemically homogeneous, that then split up in processes that are poorly understood in the early solar system. LSST will be able to explore this in much, much more detail with probably 100 times as many asteroids over a large range of distances. So this gives you sort of a flavor of some of the scientific questions that I've talked about. And what I'm going to do now is tell you about the LSST itself, and now we're going to sort of go into engineering mode, as it were. So LSST. So what is LSST? It's a 6.7 meter survey telescope to study all these questions. And it's going to be built on Cerro Pachon. It's in the Chilean Andes. Those of you who are familiar, the Gemini telescope is also on Cerro Pachon. The SOAR telescope is on Cerro Pachon. LSST it's about 1 kilometer from one to the other. And this picture, I believe, was taken from the point of view of Cerro Tololo, which is another observatory, which is just one mountain over. And so here's a picture of the mountain ridge, and here is the artist's conception of what it will look like with the backdrop of the Chilean Andes. And for those of you who have ever been lucky enough to go there, I mean, it really is a dramatic countryside indeed. So let's talk about what this will look like. It's a really unusual design, and the reason is because we want a large telescope, so large light gathering power, but again, we want that large field of view. And indeed, the design gives us 9.6 square degrees, which is an enormous number. For context, the full moon is 1/4 of a square degree, roughly. So this is something like 40 full moons. And in order to get good image quality across that enormous field of view, you have to play some very clever optical games. And so here's the design. There's a primary mirror. This, from here to here, is actually 8.4 meters. But the primary mirror is just this outer ring here. The light from this outer ring then falls onto the secondary mirror here, bounces onto the tertiary, which is here, and then into the camera. And the primary and the tertiary are made out of a single piece of glass. This was the great realization that you can actually build these things together, which means that the alignment of this piece and this piece is already set. And if you get it right, which I think they did, then you never have to worry about that alignment again. And you can see the artist who made this thought they needed to make this picture more visually impressive and put in clouds, which of course astronomers don't like. But nevertheless, there we are. Okay, so It's one thing to look at computer realizations, but this piece of glass actually exists. This is a picture from 2009 or 2010. This is what 8.4 meters of glass actually looks like. It is enormous. And various LSST folks were here. I actually missed this meeting, so I am not in this picture. Maybe there's some people here in the room who were somewhere in this picture. But that was before polishing. Now the polishing gets the detailed figure, and particularly you can see in this picture the outer part, the primary mirror, and then this discontinuity in slope corresponding to the inner mirror. And that grinding and polishing was completed in January, just 8 or 9 months ago. Here's another picture of it. Now I am in this picture, and there's various interesting people, but let me point out Roger Angel, who's the guy who came up with that design. He's an optical telescope design genius, and indeed is the brains behind the Stewart Observatory Mirror Lab, where this was done. And the mirror itself is in the foreground. This picture, unfortunately, doesn't show you the full extent of it, but gives you, again, a sense of the scale. There's various interesting people here, but let me also point out Charles Simonyi, who gave $20 million to this project. And that $20 million is what his $20 million plus his good buddy Bill Gates gave $10 million. And that is the money that allowed us to go ahead and start building this before the NSF and the Department of Energy formally said that they would go ahead, and building the mirror is indeed the longest lead item, but it's done. It's done. This is now sitting in a storage crate outside the Tucson airport, waiting to go to Chile. It'll be some years before Chile is ready for it, but we'll come back to that in just a bit.
You want to point out what Charles did to make his fortune? Do you know?
He invented Excel, right?
He was part of the initial design and developer for the Office suite of applications,
Right.
Word, Excel, and so on. Right?
Okay, yeah. So that's why Bill Gates is on his speed dial, and he's a man of means, as they see, and very, very interested in science, and you can talk to him about the science, and he knows this stuff. Even though his background is computer science, he's very interested in the astronomy. Okay, and the secondary mirror is cast, and I'm actually realize this statement. I don't know, Ed or Ethel, if either of you know if polishing has happened. I'm feeling slightly out of date on that. Okay, we can things that may have gone forward. So the camera has to have a field of view of 9.6 square degrees, and it's big, 5.5 feet tall. This is just showing that it's a complex design. Indeed, if we remind ourselves back here, that it doesn't quite. There's a lot of optics in here. There's multiple optics. It's actually not as clearly shown here as I had thought. And the focal plane is huge. So this is actually as a mock-up of the focal plane. It's this big, paved with silicon with pixels, something like 3.5 gigapixels, 189 CCDs. And one of the challenges of LSST, indeed, is to read this entire array of 3.5 gigapixels out in 2 seconds. And a normal number for a single CCD is 30 or 40 seconds. That's a typical thing. If you go to an astronomical observatory, we want to get 189 out in 2 seconds and do it in minimizing noise. And indeed, those engineering problems have been largely solved. So LSST will measure in a series of different filters. So wavelength on the x-axis and the throughput of different filters on the y-axis, and the different versions of these plots are, well, we're seeing the effects of the filters and of the atmosphere, whose transparency is not 100%, and all the reflective surfaces within the telescope. So for those of you familiar with the Sloan Digital Sky Survey, it's very similar to the filter set that was used there, but because the advances in CCD technology, the sensitivity into the red is larger, and so one can split what SDSS had U, G, R, I, Z, and we could add one more. We can split the Z filter into a Z and so-called Y filter going all the way out to 1 micron. We're limited. We can't go bluebird with this because the Earth's atmosphere doesn't transmit. That's the ozone layer. That's a good thing. And on this end, we're limited because CCDs, just because of the silicon band gap, are incapable of going beyond about a micron. And so that sets the cutoff there. So we're getting the full range that we can get from a ground-based telescope with CCD technology. So things are happening. We had the so-called Primera Piedra event in April 2015 on the summit. Here's various famous people standing here clapping, being very impressed by this large piece of rock, which is called the first stone. There it is. And I was sitting over here at this event, and the actual mountaintop is literally a 5-minute walk from right here. And so this was a big event. Michelle Bachelet is president of Chile and gave a speech, quite knowledgeable speech, I must say, about the role of astronomy in Chile. I was really quite impressed at the level I could follow the Spanish, which was not very well, but okay. And the site has been leveled. So again, at that same day, this is my wife and I standing on the summit. The previous picture is, again, just below us here, smiling, and you can see the beautiful Chilean Andes behind us. And it was our 25th anniversary, so it was particularly nice. So there we are. And here's a picture, that was back in April, roughly the spot where we saw Michelle Bachelet and the others. That site has now turned into this. Concrete is being poured. You all may have heard about the rather sizable earthquake, 8.3 on the Richter scale, just a few weeks ago. There was no serious damage here. I mean, the worst thing that happened, at least as far as LSST was concerned, was that a few big boulders fell on the road, and they had to clear those out before they could bring equipment. So that was non-trivial, but no one was hurt, and no damage was done here. So that was a great relief. So the telescope itself has a very fast, compact design. Fast is good in astronomy. Fast means you have a very squat telescope, and there's a variety of advantages of that, the most important being that the structure you have to build around the telescope is much smaller, and you save a lot of money. But it does mean that the telescope, the curvature of the primary mirror has to be extreme, and so the polishing of that was really a challenge. But as I said, that's a challenge that is now behind us. And here that now this puts that into context. The telescope will sit here. So that picture of my wife and I we were standing exactly right here, and the construction that I showed you a slide or two ago was starting to build up this area. And again, I think in the background are the real Chilean mountains. There's Cerro Tololo. You can see a telescope dome there, just literally the next mountain over. And there's a separate little calibration telescope that's going on. So that's what is now under construction. And again, the same artist has made many of these. This is what it's going to look like on a starry sky. But you see the little guy driving down here? All observational astronomers know that you keep your lights off. On a beautiful starry sky, you do not. So, but he wanted that visual effect, so there it is. Okay, so what is LSST actually going to do? It's going to be a dedicated 10-year survey. The time scale, again, we're under construction. Engineering first light meaning when we first get photons from the sky, will be in late 2019, and the survey proper will be in 2022. I will actually skip most of these details because it'll show up in slides later, but let me just give some numbers for those people who are familiar with working with magnitudes. The depth at the end of the survey over 18,000 square degrees will be 27.7, about 5 magnitudes fainter than SDSS. And that is an enormous step forward. 5 magnitudes, again, a factor of 100 in brightness. And crudely speaking, allows you to observe things 10 times further away. So one of the questions that we find ourselves talking a lot about now, and it's very much a question very much on our minds now, is LSST. It's one thing to say we're going to map the sky, but the details of how we're going to do that, when are we going to observe what, and how often are we going to come back, ends up making a real difference. I made this sort of blanket statement early on, the same data set will be great for everybody. And that's true to first order. But to second order, you know, if you're an asteroid person, you want to make sure you get the orbits of the asteroids, and that tells you that you need to come back every and then people argue, is it you come back twice a night, is it 3 times a night? If you're a supernova person, you want to come back every 4 nights and change the filters. If you're interested in weak lensing, you want to do it a different way, and so on and so forth. And so we're now in the middle of discussing how this all will work. So what do we want to do? We want to go deep, wide, and fast. We want to survey the faint universe over a huge solid angle, a huge chunk of the sky, and want to do so repeatedly to look for all those variable objects, moving objects, and average over all kinds of systematics. So the main survey will, again, I had this number on my previous slide, cover about 18,000 square degrees. In all six of the filters, we'll see a picture in just a moment. And we're under discussion doing all kinds of extra ancillary things. And rather than continuing with the words here, let's just go to a picture. So what this is a map of the celestial sphere. We're in the southern hemisphere, and so we're going to focus, for the most part, south of the celestial equator. And red means these are areas that we're going to cover a lot. This is the main survey. Each area of sky will be observed 200 times in R band and similar number of times in I band over the 10 years. In the very, very southern parts, this is what is one is looking at high air mass through a lot of the Earth's atmosphere, so you don't go you don't spend as much time here and much discussion about the details of how we will do that. Similarly here, this represents the galactic plane where the density of stars is very high, and you eventually get limited just by having a star along every line of sight, the so-called confusion limit. So we're going to not go as deep here, although again we love to argue about the details, and we want to get more asteroids in this region. So this is a realization or representation of what we might possibly do, but again the details are now under much discussion. But the emphasis throughout, it's not just quantity of data, and the quantity of data will be enormous, measured in petabytes. But there's no point in doing all this unless we're going to do it well. We really want to put the emphasis on high quality of data. And what that means, what does that mean in practice? Well, our best estimate of the distortions from the Earth's atmosphere and the distortions caused by the telescope design is that the image quality, the point spread function, the seeing, those are all words that are almost synonymous, will be about 0.67 arc seconds. Think of that as the diameter of a star image, an unresolved star image. For comparison, the Sloan survey median was about 1.4 arc seconds. So this is better than a factor of 2 better. And in fact, for many statistics, it's the area of that image that counts. So in some sense, it's a factor of 4 better just in that statistic. And of course, many more photons because you've got a much, much bigger telescope. We can probe variability from all time scales from 15 seconds. Those are our individual exposure time, all the way to the full length of the survey. We'll be coming back and back and probe that variability. We'll be able to calibrate the photometry to 1% or better. And we can measure astrometry, the measurements of the positions of stars, to something like 10 milliarc seconds, the position of any star. This is the calibration number. Sufficiently faint star, of course, one's limited by the shot noise of that image, but the calibration should be good to 10 milliarc second. And so you can make estimates of just how well you can measure the motions of stars across the sky under the dynamical influences of the galaxy, and parallaxes, which give you distances of about 1 milliarc second. And so those of you who may be familiar with Gaia, which is a satellite that the Europeans launched a few years ago, which is in the process of mapping stars at the bright end. Gaia and LSST match each other's precision at about a 20th magnitude. That's when Gaia starts dying, and Gaia really can't go fainter than that. LSST is going to push that now 4 magnitudes fainter. So we are in the process of building the science to be done with this. We wrote this book now 6 years ago. It's getting a little dated. The LSST science book, we basically told our science collaborations, said, okay, let's sit down and write down all the cool science we can do with this. And it was quite remarkable how quickly we had filled up a 600-page book, which goes on and on about all these different themes, which are different science areas. And so the LSST collaboration and the broader community have organized themselves into groups thinking about the detailed science case here. And, crudely speaking, in those 600 pages, every paragraph is a PhD thesis or two. And it's again, we wrote this 6 years ago. I was just talking to Brian. Were we to sit down and rewrite this, which I'm not sure we can pull that off, we would probably double its length. But what actually the work ahead now is thinking about not just writing down the science cases, but now trying to figure out how we would actually carry out those science projects. Okay, let's get down to brass tacks and what analyses would we actually do and how we put the resources together. So, and one of the fun aspects of this that folks here in this room will appreciate is that we're bringing together the astronomical and particle physics cultures, which, as you know, are interestingly different. And so we have really quite amusing conversations about the way funding actually works and the right way to build collaborations and all those fun things. Okay. Okay. Well, actually, this is very much up NCSA's alley. NCSA, the current plan is that NCSA will play an absolutely key role in operations of LSST, and will be the data will flow from Chile to here, and the image processing will be here. So what does the image processing consist of? Certainly the philosophy of that image processing is that most of the science, I put this in quotes because people love to argue about this, but most of the LSST science will not be done by people getting the raw data and trying to reprocess it themselves. That would require everyone downloading tens of petabytes onto their laptop, and that would probably not be a good way to go. But rather, the pipelines that are being developed now will measure the properties of every detected object and measure them in the most statistically meaningful and robust way, and then produce massive catalogs with all the tabulated quantities that have been measured. And most of the idea is that most of the science could be done with those catalogs, statistical analyses on those. And again, NCSA is going to be front and center in that. The current pipelines are under development. They're currently at the level of what the SDSS has done, and they're rapidly getting better. I mean, they're going beyond them in a variety of ways, and I'm happy to talk to anybody who would like to know a little bit more detail about that. So the idea is that the data will be released to the US and Chilean communities. I should have said, this is, of course, a US project being built in Chile, and so US and Chile are the two principal partners. And so the data will be free to anyone in the US and Chile. And if there's time, I can talk about the rest of the world and how they will fit in. And the data will be released in two different forms. One is that we want to ask the question, we've taken a picture of the sky, did anything explode? Did anything change in that? And so what's going to happen is we'll take that image, we'll take the difference of that image to a reference image of that same area of the sky, see what changed, and immediately release. By immediate, I mean within 60 seconds. So very fast processing. That will not happen physically here. I think that will happen in Chile. Is there? It is happening here? It is happening here. So we'll come all the way here, and the processing will happen here. Okay, so I misspoke. Yes. And then you will be able to get an alert on your phone, should you so desire, saying an exposure happened 60 seconds ago, and here's an object that changed. You probably don't want to do that because we're guessing there'll be several million such alerts per night. And so what you're actually going to want to do is put some rather heavy filters on that. And there's much discussion about how that will work in practice. But so if you want to go find the star that just exploded, so you can observe it with some other facility, for example, you will get that information really immediately. So that's 60 seconds. The other relevant time scale is a year. There we're taking differences of images. Here we add up the images. We process all the data to date in a stacked way and co-added. This turns out to be a loaded word. And if anyone wants to know the technical details, you can ask me about it. The proper way to take multiple images in any given area of sky and process them all together. And process self-consistently, and again, release to the world. And so that in our jargon, this is called level 1 and this is called level 2. We also have something called level 3, whereby folks can write their own software to process these data, and that will be, and they can run it on the LSST platforms. Okay. What am I doing on time? I think I'm going to skip this. I could talk further about the software, which may be of interest to folks here, but what I want to do is jump on and talk about what's happening in the rest of the world, or at least things that I'm involved in. LSST is great. It's 2022 is still some years away. We'd all like to do make wonderful astronomical discoveries in between. And so there's a variety of things happening on a variety of fronts, but I want to talk about the ones, these two closely related projects that I'm involved in. So this is the Subaru telescope on the summit of Mauna Kea in Hawaii. It is operated by the National Astronomical Observatory of Japan and is distinctive. It's a 8.2 meter telescope and is distinctive for having the largest field of view of any of the 8 meter class telescopes in the world. It will only be surpassed once LSST is built. And so there are two instruments which I'll now introduce. Precursor PrimeCam, which is an imaging camera, very similar in spirit to LSST, and the prime focus spectrograph, which is under construction to do spectroscopic observations for the Subaru telescope. So the project overall has this highly clever acronym, Subaru Measurements of Images and Redshifts, which comes out in Japanese, Sumire. And those of you who speak Chinese, that is the character. It means, the Japanese word refers to the flower, the violet, and the inspiration for this comes from here. This is a izakaya near the University of Tokyo. Ed Turner, though some of you may know him, this is his favorite place to hang out at the University of Tokyo. And there it is, Sumire. And Ed goes there every time he goes to Tokyo. He's now quite good buddies with the proprietress of this place. And so the story is, I was not there, but Ed had taken David Spergel and several of the Japanese to this place. And they're saying, we need a name for this project. And Sumire, well, Su sounds like Subaru. And then after some beers, I think David Spergel invented this acronym. And so that's the name of the project. This, I was looking this up, this expression, okigari in Japanese, means relaxed, carefree, laid back, something like that. So there we are. Okay, so let's go back to the astronomy. So Precursor PrimeCam. So Subaru 8.2 meter telescope, one of the largest telescopes in the world, and with the characteristic that the optics of that telescope support very wide field imaging. So Precursor PrimeCam is an imaging camera built by Satoshi Miyazaki and his team at NAOJ with these characteristics, 1.77 square degrees. It's not quite 9.6 square degrees of LSST, but it's still impressively large. And indeed, I said the optics support wide field imaging, but you still need quite a bit more optics. This is the actual camera, all the optics you need. This thing is 10 feet tall and 3 tons, I believe. And here's a picture of the focal plane with 104 CCDs on it. It's really quite an impressive thing. Again, LSST will blow this out of the water, but this thing exists. And LSST is currently concrete being poured on a mountaintop, so it's still many years away. So we're in we meaning Princeton, the folks in Japan, and folks in Taiwan are in the process of carrying out a survey with the Precursor PrimeCam. I won't talk through this in detail, except to say, so maybe I will. Okay, what's plotted here? Area of different surveys. Each dot here represents a survey. Area of different surveys on the x-axis, how deep these surveys go on the y-axis. HSC will actually have 3 different layers, which are shown here. Where do you want to be? You want to be in the upper right, with large area going very faint. And here's what LSST will eventually do. Where's SDSS on this? SDSS is way down here. Much shallower, although covered a huge area. And again, so this puts HSC in the context of the surveys that are out there and shows that especially if you're interested in going deep over large areas, HSC is the best thing going, again, until LSST comes along. And has a filter set very similar to that of SDSS and, for that matter, LSST. And we could discuss the details if people are interested. 1.77 square degrees is a big number. And this is a picture of the Andromeda Galaxy taken in a single shot with Subaru. So cheating a little bit because it's actually 3 different filters. So it was actually 3 shots. But anyway, you get the whole, you get the whole galaxy in one shot. You've probably seen pictures of the Andromeda Galaxy before, but you have the dynamic range of angular scale that you can zoom into a small patch and see individual stars and faint background galaxies. So you get the huge size and the great detail. This is details about the sky coverage, but let's go to this picture. So here's a picture of 0.01% of all the data we have thus far. And so imagine this multiplied by 10,000. And it shows, this is a 5 square arc minutes in the cosmos field, taken with a hypersuprime cam, with image quality that's about 0.6 or 0.7 arc seconds, which is extremely good in this game. And this is what LSST data will look like. But we're getting it now. Again, we're not going to go quite as large an area, but it's just amazing looking at this. There are galaxies everywhere. It's just, for those of us who like galaxies, we just look at this. And if I had more time, I would bring up the larger picture from which this is shown and pan around. Again, people have taken pictures to this depth before, and what makes this special is the fact that we have this over many square degrees. And I can't show you that because of course, to show you how wonderful the data are, you have to zoom in, and you can only see a tiny fraction of it. So anyway, I find that really fun to look at. Okay, this is just showing that we're covering the data. Let me just show this off. This actually shows the histogram of the seeing that the image quality that we've gotten with hypersuprime cam thus far in the roughly 40 nights that we've had. And the median seeing in the I-band is about 0.6 arc seconds, which is, again, an amazing number. Which, again, this is better than what LSST is even claiming that it will do. So the proof will be in the pudding for LSST, but Subaru is already doing it. So that's pretty impressive. Okay, I'm going to skip that. This is just another shot image comparing SDSS images here. Remember, I had a limit of 22.5 or 23 versus hypersuprime cam images. It's the same field, three different fields here, and you get a sense of just how much deeper and how much more detailed information you get. So that's a fun way to look at this, and we could spend some time enjoying all the wonderful structures in galaxies that are apparent in this. Given the time, I'm going to skip that. Redshift quasars, and talk about the other aspect of the SUMIDAD project, which is called the prime focus spectrograph. So this is under construction. The metal is being cut as we speak. The Sloan Digital Sky Survey, I didn't emphasize this earlier on, had the main survey has had two components, the imaging survey, which I've been focusing on, but also spectroscopic survey, where you can measure spectra of galaxies, give you redshifts and therefore distances, and then detailed physical characteristics. And so the prime focus spectrograph part of the project is asking the question, can we do something similar in Subaru? So we're in the process of building 4 identical spectrographs, which in many ways have a design similar to that of the SDSS spectrographs. Each one will take 600 fibers, so 2,400 fibers altogether, with a field of view, it's not written here, of 1.2 square degrees. And so we can observe 2,400 galaxies at a time on one of the world's largest telescopes. And this is just a schematic of the spectrographs, one of the 4 spectrographs. Those of you who are familiar with the SDSS may know that we used a dichroic to split into 2 different bands, a red and a blue channel. Here we're actually using 2 dichroics and splitting into 3 bands, a red, a blue, and an infrared camera. And so let's get some of the, I'll come back to this slide in just a moment. Here are the characteristics, just under 2,400 fibers, 1.1 square degrees, I said that not quite right, and a wavelength coverage from 380 all the way to 1260 nanometers, which is really an impressive value, and very high throughput throughout. And this shows a schematic of how this all fits together. 4 of these spectrographs, we saw the schematic of one of them. This, at the top end of the telescope, is that same wide field corrector that you saw for hypersuprime cam, that same 10 feet tall, 3-ton monstrosity. Oh, here it is, it's the same picture. And then the fibers themselves sit on top of that and are individually positionable, and then huge amounts of fiber cable take you from the top end of the telescope is not quite shown here, all the way to a room on the side where the spectrographs live. So, and we'll get wonderful data, but we're planning a 300-night survey starting in roughly 2019 on 3 major science themes: cosmology, doing a large-scale redshift survey mapping the distribution of galaxies, study galaxy evolution over a large range of redshifts, trying to learn about how galaxies evolve, and again, structure of the outer parts of the Milky Way, including with spectroscopy, you get their kinematics, their motions, and you get their detailed chemical composition. And so again, a 5-year survey starting in 2019, I will advertise right now, we're looking for new partners. And I was talking to Brian a little bit about possibilities there. So, my last slide, and I'll finish a minute or two later than I had thought. So, what are the opportunities here? There are many. Start thinking about LSST science. The LSST science collaborations are open to everybody, and anyone who wants to know the details of how to join, just come talk to me. Hypersublime Cam, we're taking data now. Our first public data release will be in March 2017, so those data will come on. The PFS collaboration is looking for new partners, and we'll see if there's any interest here. And just as a final thought, surveys really have been an enormous engine of discovery in astrophysics, and will continue to be so. And by putting LSST as its highest priority, the U.S. community has sort of put its money where its mouth is in the statement, and said that that's where we want to grow. And if the surveys are done well, as I think we're going to do, these are going to have scientific impact far beyond whatever we said the LSST would do. I'll finish there. Thank you.
If you have a question, please come to the microphone.
You talk about the filters. I don't understand the filters. It's like the temporal resolution.
Whoops. Okay. I'm sorry. We're talking about the LSST filters?
Yes.
Let me bring that slide up. Sorry, we're going to go backwards for a long time.
2 seconds. You want to?
I'm sorry?
You said like the temporal resolution is 2 seconds.
No, 2 seconds. Sorry. Are we talking about the filters that go in front of the camera that?
Yeah.
Yeah.
Is there like mechanical? You just change them?
Or? No. So typically, yeah, I said that there's 2 seconds between exposures, but no, you can't take one huge piece of glass and move it in and out in 2 seconds. So typically, what you will do is most of the time you stick with one filter for an hour or so. Say, okay, we've had enough of this filter, and we'll switch to another one. And that overhead, I think, is about, I'm looking to see, 2 minutes. It's 2 minutes. Yeah, so every hour or so you get that 2-minute overhead. But most of the time you're working with a single filter.
Okay. Yeah. Thank you.
Thanks. So, as you've pointed out, both Sloan and LSST were multi-decade preparation kind of things. So, what's next?
What's next? Well, Brian and I were just having this conversation. So, LSST will finish in 2032. At least that's the plan. And in 2032, we'll have a state-of-the-art telescope with what may no longer be quite state-of-the-art camera at that point, but all kinds of wonderful science that we can imagine doing. The time scale on which to start figuring that out is now. This Decadal Survey process is the mechanism by which the community can start thinking about that. So the next Decadal Survey will be in 2020, which means now is the time to start thinking what that Decadal Survey will say. So there has been very little discussion, in fact. There's been everyone asks this question, like, okay, what are you going to do next? But there's been very little formal discussion about what kind of ideas might we think about for this state-of-the-art telescope. Telescopes, the historical record tells us that telescopes typically last 50 years. That is, after about 50 years, you start thinking, okay, I've gotten everything I can get out of this telescope, and I want to think about replacing it. And again, we've got a plan for the 10 years. It would be very naive of us to write down a scientific case for what's the most interesting thing to do in 2032 now, because if we were to do the equivalent of going back 17 years and ask what's the most exciting science we should plan for the year 2015. If we're asking that question in 1998, we would write down all the wrong things, or at least extraordinarily naive things. So on one side, we want to ask that question from a position of knowledge and all the things that we will learn from LSST and all the other wonderful things that are going to happen over the next 10 years. On the other side, as you say, these projects have enormous lead time. So this is a very wishy-washy answer to your question, but the onus is on all of us to actively start thinking about that and organizing ourselves to start putting together some plans.
Right. So I guess I was actually asking about new hardware. So,
Yes.
So after LSST, do you want to go to the infrared? Do you want to have a 30-meter telescope that covers 100 square degrees?
Yes.
What's the next thing?
No, those are exactly the questions that need to be answered. And my quick answer to that is yes, all of the above. That would be lovely. And then the other thing we know, of course, is that financial constraints are really an enormous part of this whole story. With the Decadal Survey, they had to work within some envelope of realism, and so they had their optimistic, okay, and pessimistic scenarios, and even their pessimistic scenario, in retrospect, was actually quite optimistic. And we could get into a long story about funding of science in the U.S. and other such things. But and how to think about that in the timescale of 2032, I don't even know how to, what order of magnitude of things can we imagine doing? And part of the challenge, the good thing, of course, is that the astronomical community continues to grow and people are ever more ambitious. The flip side of that is that the toys we want to build get ever more expensive because we want something that's even larger and more capable and so on. So that's, again, I'm not answering your question, but just pointing out some of the issues that one has to think about as one goes forward.
So it's an amazing project, and thanks for a very clear explanation, at least for me. But I was curious, you mentioned some of the funding and contributions you received, but what is the funding for the entire project, and how much is in actually deploying, and how much is in operating, and what things are in the operating side of that?
So the quick answer is that for the construction project, that key money from Simonian and Gates, which I mentioned, the $30 million, allowed us to start building, allowed us to do the primary mirror, also allowed us to start preparing the site in advance. But the main chunk of construction comes from about 2/3 from the NSF, the building of the telescope and the data systems and the software, and the Department of Energy, which is building the camera. And so that's roughly 2 to 1. That's for construction. For operations, the plan now is that, again, there'll be a 2 to 1 split between the NSF and Department of Energy, and those two together will cover about 3/4 of the cost. The last quarter will come from the international partners, which we're in the process of gathering. Ethel knows all about this. So the current, I quoted a number of $1 billion. That was construction plus 10 years of operations. The operations budget currently is $36 million a year for 10 years. And so again, NSF plus DOE will cover roughly $30 million of that. No, 28. And the last 8 to 10 will come from international partners. And so that's where we are right now. And the detailed story of those international partners is a very long one, but requires several beers for Ethel and me. So, yeah.
Well, if there's further questions for Michael, we have the reception outside, so please join us. And thank you again, Michael, for conveying the excitement of LSST.